Welcome to the Explainer. Today we're tackling one of those puzzles in physics that just seems impossible. For almost 100 years, it's had physicists scratching their heads. How does a perfectly symmetrical, spherical explosion at the quantum level produce something as clean and definite as a single straight line? It's a question that really forces us to ask what reality even is. Okay, let's get right into it. So, picture this. On one side, you have the beautiful, pure math of quantum mechanics, and it tells us, without a doubt, that when a radioactive nucleus decays, the particle it spits out should be a perfect wave, expanding outwards in all directions, like a ripple in a pond, but in 3D. A perfect sphere. But then you go and actually look at it in an experiment, and what do you see? Every single time, a single, sharp, dead straight line. It's a total contradiction. And hey, don't just take my word for it. This isn't some newfangled problem. All the way back in 1929, the guy who the problem is named after, Sir Nevill Mott, basically said, yeah, this is really hard to wrap your head around. This is the kind of deep paradox that kept people like Einstein up at night, this bizarre clash between the fuzzy, probabilistic world of quantum theory and the solid, definite reality we actually see.
Right, so to really understand what's going on, we have to go to the scene of the crime, if you will, the cloud chamber. A cloud chamber is this incredibly clever device. You can't actually see the subatomic particle itself. It's way too small, but you can see the trail it leaves behind. As this high-energy particle zips through a special kind of vapor, it literally knocks electrons off the atoms it passes, leaving this trail of charged ions. And instantly, the vapor condenses onto those ions, forming a tiny visible line of mist. It's like seeing the contrail of a jet you can't see. And for an alpha particle, that trail is always straight.
Now this is where it gets really interesting. That whole spherical wave idea, it's not just a nice guess or a convenient model. It's basically a non-negotiable demand from the laws of physics themselves. The universe insists on it.
And why? Well, it all comes down to some of the most fundamental rules in the cosmos. Things like conservation of angular momentum. You can't just create spin out of nowhere. When you look at the specific type of decay we're talking about, and you run the numbers through these bedrock conservation laws, you get exactly one possible answer. The alpha particle has to come out with zero orbital angular momentum. No wiggle room.
And a particle with zero orbital angular momentum has a special name. Physicists call it an S-wave. And here's the kicker. An S-wave, by its very definition, is perfectly, flawlessly spherical. There's no preferred direction. No up, no down, no forward. Just an equal probability of going everywhere at once. So you see the problem. The fundamental laws of physics are screaming sphere, but our lab equipment is screaming line. The paradox is real. So you have this epic standoff between theory and reality. How in the world did Nevill Mott crack this thing? Especially way back in 1929.
Well, his genius was that he didn't try to just brute force an answer. He completely reframed the question. Instead of asking how a sphere becomes a line, he started to wonder, what if we're not even looking at the system in the right way? What if the problem isn't the physics, but our perspective?
He had this incredible insight that everyone was stuck thinking in our normal, everyday 3 dimensions. But to solve a quantum problem, you have to think like quantum mechanics thinks. And this is where your brain might start to melt a little, but stick with me. Mott realized the mistake was thinking about just the alpha particle. The real system, the quantum system, is the alpha particle plus every single atom in the gas of the cloud chamber all interacting, all part of one giant quantum state. And this combined reality, it doesn't live in our 3D space. It exists in this vast, abstract mathematical landscape that physicists call configuration space. So, in this huge, high-dimensional space, that initial spherical wave of possibilities starts to interact with all the atoms. And just like waves on a lake, these quantum possibilities can interfere with each other. They can add up, or they can cancel each other out. And what Mott's math showed, brilliantly, is that for every possible zigzag or curved path, there's another one that's exactly out of phase and cancels it out. They just vanish. The only possibilities that survive, the only ones that line up and reinforce each other, are the straight lines. So the track we see isn't the path of a particle. It's an interference pattern. It's the only outcome left standing after all the other possibilities have wiped each other out. Mott's idea was a revolution. Today we call it decoherence, and it's a cornerstone of modern physics. But, as it so often happens, solving one giant mystery just uncovered an even deeper one.
Let's think about it like this. Mott's solution tells us why the menu of possible realities only has straight line on it. That's what we call the emergence problem, and it's pretty much solved. But it doesn't tell us why, in any single experiment, the universe chooses that specific straight line, the one pointing at 2 o'clock, instead of the one pointing at 10 o'clock. That's the selection problem. And folks, that is still one of the biggest unanswered questions in all of science.
Because see, even though decoherence guarantees the outcome will be a line, it doesn't break that initial perfect symmetry. The total probability of seeing a line in any direction is still a perfect sphere. The universe has this menu of only straight lines, but it has no preference for which one it picks. So how does it choose?
To even try and answer that, you have to basically pick your favorite flavor of quantum mechanics. The traditional story, the Copenhagen Interpretation, just says, well, the universe randomly picks one when you measure it. It just happens. Another view, called Bowman mechanics, says there was a hidden piece of information from the very beginning that secretly guided the particle along that specific path. And then there's the wildest idea of all, the many worlds interpretation. It says there's no selection at all. Every possible straight line track happens, each in its own parallel universe.
And this, right here, is why a nearly 100-year-old physics problem is maybe more important today than it has ever been.
Because the Mott problem isn't just about a tiny particle in a box. It's a perfect miniature version of the biggest question in all of cosmology. How did our universe, full of galaxies, stars, and planets, emerge from the perfectly smooth, uniform, featureless state it was in right after the Big Bang? It's the exact same puzzle, just blown up to a cosmic scale. How do you get structure and complexity out of perfect symmetry?
And when you're talking about the entire universe, that old Copenhagen story about a measurement causing a choice runs into a huge wall. I mean, who's outside the universe to measure it? Nobody. The universe is a closed system. It has to sort itself out from the inside. And that's why Mott's approach, treating the entire system as one big quantum whole, is so powerful. It's really the only framework we have that can even begin to tackle how our own reality came to be.
So you see, the Mott problem is way more than just a historical quirk. It really is our cosmology in a bottle. It's a tiny, manageable experiment that lets us probe the deepest mechanisms of reality itself. It shows us how the classical, structured world we live in can emerge from the inside out, born from the strange and beautiful rules of the quantum realm. And so that humble, straight little line in a cloud chamber forces us to stare right into the biggest questions imaginable. Is the reality you're experiencing right now the result of a single, random roll of the cosmic dice? Or is it just one page in an infinite book of stories, with all the other possibilities playing out in parallel? The Mott problem doesn't give us the final answer, but it sure gives us a profound and beautiful way to ask the question.